at Sungkyunkwan University in person and give a talk, and then meet with all of you in person. Although the Professor Park was just here in New York City visiting me at NYU, so the Professor Park, we already met like 2-3 days ago, and then somehow we are here across the Pacific. What a world, right? So today I decided to focus on one particular paper that I recently have written together with my PhD student Ethan Paris and my collaborator Dao Killa, who is now at Facebook AI Research, on analyzing what this big fuss that arises from the availability of GPT-3 from OpenAI in recent years. In particular, we focus on this capability of fuchsia learning using a large-scale language model. So in order to talk about this, we need to talk first about what we mean by fuchsia learning. When we say fuchsia learning, what does that actually mean? First, let me tell you about what I thought fuchsia learning was as a machine learning researcher myself. So in machine learning, it's not really a new concept. People have been looking into this ability of fuchsia learning, or sometimes even zero-shot or zero-data learning, from about 2005 or 6, or perhaps we can probably find some more earlier examples as well. But in fuchsia learning, the goal is to build this so-called fuchsia learner that is going to take as the input a small set of training examples, and then based on those small number of training examples, this fuchsia learner is going to return the model or the primary configuration of a model that can be used in order to classify a new example. And then that model, we're going to use G to refer to that model. And of course, it's a fuchsia learner, which means that it is a machine learning algorithm on its own. What that means is that this machine learning algorithm has its own hyperparameters or the parameters. So there are a number of components here. The first one is that we have a fuchsia learner that is parameterized with a set of hyperparameters. And this fuchsia learner takes as the input a small number of training examples. And given this small number of training examples, the fuchsia learner returns a parameter configuration that's going to be used by this actual model G to classify a new example X prime into one of the categories. So this is fuchsia learner in a sense that it turns a small number of examples into a model that has learned from this small number of examples. Now, there have been a number of recent approaches that have tried to tackle the problem of fuchsia learning using the paradigm of deep learning. One of the representative example is prototypical network from Snell et al. 2017. And in this prototypical network, the goal is to learn a feature that's going to allow us to easily identify to which class the new example belongs. In this prototypical network, we start with preparing a number of as in more than one, small sets of training examples, and then often we call them as a fuchsia training data sets. And this prototypical network is going to learn to output the set of parameters, phi, that I'm using here, that's going to be the parameters of this embedder. And what this embedder does is to given a new set of few examples, this embedder embeds each and every one of these n-many, very small number of examples, into a so-called prototypical vectors, or the prototype vectors. And once we have these prototype vectors and the new example x prime, all we need to do is compare each and every prototype vectors against the new example x prime using the dot product. And whichever the prototype vector that's going to have a higher dot product value against the x prime is the class to which this x prime, the new example, belongs. Another recent approach that has become extremely popular is called model agnostic meta-learning, or MAML in short, by Fin et al. 2018. In this MAML, just like in prototype network, the algorithm takes as input many fuchsia datasets. And then based on these fuchsia datasets, MAML returns the initialization of a deep neural network that's going to be used as a starting point of using stochastic gradient descent together with a small number of examples that are going to be given in the test time. Of course, the end state of stochastic gradient descent is the theta, the parameters that are going to define a neural net that learns to classify a new example x prime into one of the desired categories. Now, across these two examples, you notice one thing. In order to do few-shot learning, what you need is a set of few-shot training sets. This is a bit different from usual machine learning when we think about just having a one large training set, which consists of individual examples. Now, because our goal is to come up with a few-shot learner that is able to work with a small number of new examples in the test time, we also need to have a training set of few-shot training sets. So it becomes a bit meta. There's a reason why we call it meta learning. So from this perspective, few-shot learning is really nothing that different from supervised learning. In fact, one might even say that few-shot learning is equivalent to supervised learning. Why is this supervised learning? We have a training set that consists of few-shot training sets. We have a validation set that consists of few-shot validation sets. We have a test set that consists of few-shot test sets. And we have parameters and the hyperparameters. So really, it's exactly like supervised learning. Only difference is that each and every example here is not just a single vector or a single image, but it is in itself a set of other examples. Because it's supervised learning, if you wanted to solve the problem of few-shot learning, assuming that we have access to all those training set of sets, validation set of sets, and test set of sets, we just follow a usual practice of supervised learning. We're going to train a model, train a few-shot learner, and in order to train a few-shot learner, we use the training sets from the training set and the hyperparameter. We need to have a hyperparameter. And in the validation stage, we try to decide on the hyperparameter that is used to train this few-shot learner. And in the test time, we use a test set of test sets in order to see how well this few-shot learner is going to work on a small number of new training examples and using them in order to classify a yet another new test example. So in a sense, really, few-shot learning turned out to be exactly equivalent to supervised learning. What this actually means is that sadly, there's no such thing as free lunch. We really have to run all three steps, that is training, validation, and testing, even when we work with few-shot learning. We can't really get away with any of these stages. We just really have to follow every single stages in order to train properly our few-shot learner, select properly the hyperparameters that are used for training a few-shot learner, and in order to report properly how well this few-shot learner is going to work in the test time. And this is just inevitable because this few-shot learner has its own parameters, and to estimate that own parameters, we need to be able to select the correct hyperparameters as well. And then this is really inevitable. It's not only for few-shot learning. Whenever we are talking about working with the multiple test sets or the multiple test scenarios, such as in transfer learning, multilingual learning, multitask learning, and whatever other possible paradigms you can imagine, you always run into this issue that you cannot avoid any of these three stages. You really have to stick to every single one of them. There's no free lunch. So let's look at the two earlier approaches that we just talked about from this angle. Now, in prototypical network, which does a feature learning, the prototypical network works as if it's running a meta-training and meta-validation. So meta-validation allows us to choose the hyperparameters used by this prototypical network, and then using that hyperparameters, we run meta-training in order to result in this embedder that is a Fuchsia learner returned by prototypical networks. And then there's the meta testing stage, where now we have to use a new test set of few examples in order to see how well this embedded works on yet another example. So we do have the meta training, meta validation, and meta testing stages. Same thing with MAML as well. Now MAML algorithm is going to find the initialization for the SGD in the meta testing phase using two stages, meta training and meta validation. What does meta validation do? It's going to find the hyperparameters that are used in order for MAML to figure out this initialization. So exactly just like prototypical networks, we have meta training and meta validation stage on the left side of the site, and then there's a meta testing where we have to use a held out set of training sets in order to see how well this meta learner or the Fuchsia learner works. But then the thing is, unfortunately, it's much more tricky to properly evaluate Fuchsia learning compared to a usual supervised learning, even though Fuchsia learning is equivalent to supervised learning. Why is that? First, we now have to collect or synthesize a set of data sets. So in usual supervised learning or the usual conventional setting, what we need to collect is a set of examples. That's already difficult, but if now we have to work with collecting, we have to collect a set of data sets. Furthermore, we have to be much more careful about information leakage across training, validation, and test sets of data sets. We have to ensure that all those examples that belong to all those sub-data sets do not overlap across training, validation, and test sets of data sets. And then these two things are not really easy to do in practice. However, that doesn't actually excuse us from skipping over some of the steps or just letting the information leak from training validation to test stages. So we have to be really careful here. And the difficulty actually is pretty apparent from the fact that there aren't that many benchmark data sets or the benchmark scenarios that have been proposed for Fuchsia learning, even though in machine learning, what we do is to come up with a benchmark as rapidly as possible, and then given any new benchmark, let's try to beat the hell out of it as quickly as possible. That's what machine learning community does, and then how machine learning community has grown. However, in the case of Fuchsia learning, it has been much slower in terms of this kind of progress, because it's just very difficult to create a benchmark or the data set of data sets. This is how I have viewed and then what I thought Fuchsia learning was until last year, when OpenAI, Brown et al., claimed in their abstract saying that the GPT-3 can be used without any gradient updates or fine-tuning, with tasks and Fuchsia demonstrations specified purely via text interaction with the model. So what that means is that they claim that they build a large-scale language model with which we interact using language alone. And this language model, GPT-3, can solve many problems, in particular in the context of Fuchsia learning. This is awesome. And then they actually had a number of examples in their paper. I highly recommend you to take a look at it, although with a gigantic grain of salt. Let's look at some of the examples, what they said. They said that the GPT-3 can translate English to French without learning or without us explicitly teaching it how to do so. All we need to do is just tell GPT-3 that translate English to French, and here is the English word cheese. And the GPT-3 is going to answer by simply saying that it's going to be fromage. And one-shot learning is where we are going to provide one particular example. We're going to say, please translate English to French. And one particular example would be that sea otter is translated to in French as le tour du mer. And what is cheese in French? And again, the GPT-3 is going to give us the answer that is going to be fromage. And then, of course, you can imagine that simply providing few more examples leads to future learning. Awesome. This is essentially the dream of NLP researchers, machine learning researchers, and more generally or more broadly, artificial intelligence researchers. But let's think about it a bit more. This sounded too good to be true, and then let's consider the case of future learning. So OpenAI provided an API access to GPT-3, which is a large-scale language model. And then what we do is that we need to come up with a few examples to solve the problem. In this particular case, the problem of translating English to French. And we have 3 examples. And then, of course, we have a new example for which we don't know the translation. And that is the text that GPT-3 should translate into French. And then what we do here is that we are going to look at these examples as well as a new example and try to create this so-called prompt or the prefix. What does that correspond to? This prompt is a way for me or us to interact with GPT-3 or instruct GPT-3 to do something, and in this particular case, to translate a given text into French. And GPT-3 is going to output the final hidden state, the vector representation, and then what we actually need to do further is to identify what are the possible target class tokens. So we're going to choose only the tokens that correspond to French. And between these target class tokens and the final hidden state, dot product is going to be computed, and GPT-3 answers by choosing the one that has the highest dot product value. Hold on. Now this is a bit weird because there seems to be quite a lot of hyperparameters here. First one is that we need to create this prompt. We need to tell GPT-3 what this task is. We need to decide how to present all these few examples to GPT-3. We also need to decide a target token set that's going to be used for GPT-3 to choose the answers. And we even need to decide how many training examples we need to collect and present. And there are actually even more of them. And there are surprisingly many of them. If you go into the Appendix G of Brown et al. 2020, that is a GPT-3 paper, then you'll see that we need to make quite a lot of decisions, or the micro decisions, in order to make GPT-3 answer or GPT-3 work as if it is a future learner on its own. And this is very different from the conventional notion of future learning that we just talked about at the very beginning of my talk. There's absolutely no training, validation, future tasks on which the future learner, that is GPT-3, can be trained. That is, hyperparameters of the future learner must be found somehow without existing tasks. That's a bit weird. Now, this would have made perfect sense if we could talk to GPT-3 as, however I want, and still GPT-3 is going to understand it perfectly, then this wouldn't have been an issue. However, we know that these large-scale language models, however perfect they are, however awesome they are not really perfect. We know that they are going to do, or they are going to interpret our instructions in a way that does not necessarily agree with how our intuition works. So we need to figure out how to talk to GPT-3. And then figuring out how to talk to GPT-3 is not that easy. So my initial reaction, which was to think that this is extremely cool, has changed it a bit. Is it really true that we can work with GPT-3 purely via text interaction when it's unclear what is the right way to interact with GPT-3? So my student Ethan Perez, my collaborator Dao Kila, and I started to look into some of the papers, including GPT-3 papers, that talk about so-called prompt engineering. That is, how to interact with GPT-3 or large-scale language models. There were a bunch of papers immediately after released, right after the GPT-3 was released. And a bunch of these papers got all these best paper awards from the various venues. That's great, so they must have done something right. So we started to read each and every one of these papers. And what we found is that how they choose these prompts or how they choose these hyperparameters were based on so-called the full development or full validation sets. What are these full development or validation sets? These are the validation of the development sets that consists of many, many labeled examples. In fact, much more than few labeled examples. And then it turned out that's true in many further papers as well. 2 outstanding paper awards recipients from NACO 2021 this year also chose the hyperparameters based on the full development set. Of course, they did not use it themselves, but they were using the hyperparameters from earlier papers that used the full development or the validation sets. So the answer to the question, do they really use only a few examples, turned out to be false. They did not use only a few examples. In fact, they used a lot of labeled examples. What this implies is that most of the recent studies on few-shot learning with large-scale language model are not really truly few-shot. What they've done is rather building a few-shot learner that's going to take as the input a set of small, very few training examples together with a lot of validation examples. And both of these are labeled. This raises a question. At what point do we call it a few-shot learning? Is this a few-shot learning because we call some of the first few examples as training examples? Or is it really just a learning? Because at the end of the day, the distinction between training and validation examples is very artificial. We just decide what we call as training, and whatever is remaining ends up being validation. So we can't really tell the difference here. Essentially, what GPT-3 or the existing, let's say earlier papers on few-shot learning with GPT-3 or large-scale language models has been using us, people, as a hyperparameter search engine. So we are going to look at a lot of validation examples, and then looking at them, and then looking at how well GPT-3 works, we were the ones who had to decide how to design this prompt so that GPT-3 is going to answer in a way that we want it to answer. By the way, I'm not saying that what GPT-3 has shown is not exciting. It's actually extremely exciting because already in 2014, while I was in Montreal, we actually had the very first glimpse at the power of neural language models as knowledge base or the question answering system that is generic enough and can be accessed via natural language. So here's an example we came up with when we were working on machine translation. In the source, we're going to give as the input some unknown token, some special token, followed by Korea is a friend of the United States, and we're going to force our machine learning system to translate this into a target, into French, but we're going to prevent it from outputting unknown token, the special token. And this translation system translated the source sentence into South Korea is a friend of the United States. Now, on the other hand, when we replace friend with enemy, and then again force our translation system to make a full well-formed translation, we switched immediately from south to north. So what that means is that this model, by being trained on a large amount of data, already had a bit of a common sense, and then by probing it or prompting it correct, we could actually uncover some of the hidden knowledge within these large models. And then because I saw this in 2014, my excitement has been always there. And then looking at what GPT-3 can do, I'm even more excited. But of course, that doesn't mean that we can be sloppy about science itself. So we can be excited about the things that can be done, but that excitement aside, we have to always be very careful about scrutinizing what are actually being done, and then what can really be done, and what will need to be worked on. So we decided to look into whether GPT-3 or this kind of large-scale language model can really be used for truly a future learning, where we really have only a few examples available for both hyperparameter selection as well as training. And hyperparameter selection here includes figuring out how to create an instruction that's going to be used to prompt this language model to do what we want it to do. And training is going to be quite straightforward. Once these prompts has been engineered as a part of the hyperparameter selection, we're going to just run the language model over this prompt and then let it generate the answer after the prompt has been consumed. Importantly, we reserve this large held out set, a large set of the labeled examples only for evaluation. We don't use them neither for prompt engineering nor training, which makes it really the truly future learning, because really only a few examples are available in the training time, including the hyperparameter selection. To build a true future learner, or any kind of future learner, we in fact need three ingredients. First one is a hyperparameter selector. That hyperparameter selector is going to take as input a set of few examples we have. These are only a few of them. And then it outputs a hyperparameter configuration that's going to be used together with a set of few examples to output by the future learner to output the parameters of a predictor that takes as the input the outputted parameters and a new example, and it maps the new example to one of the classes in the classification problem. And then what we do is we're going to try to compute the expected loss of this predictor that uses the parameter that comes out of the future learner, that uses the hyperparameters that came out of the hyperparameter selector. So truly in one line, in fact, in one equation, we can write the entire process of building and evaluating true future learner as compactly as you see on this slide. What this actually tells us, this formulation of true future learning, what it tells us is that most of the, if not all, of the recent studies that have focused on future learning for large-scale language model have not done true future learning because they were using a very large validation set for selecting the hyperparameters. And this often leads to the overestimation or the overly optimistic estimation of the actual risk or the actual performance, because this D prime tends to be a set of examples drawn from the same distribution as the distribution used to draw test examples. So it's really extremely biased, and then it's a bias in an optimistic way, and then that's never a good idea. When you're trying to build a model and then see how well it works, we often need to estimate either the average risk, that is, on average how well it's going to do on the new test examples, or we have to look at the lower bound to the accuracy that it's going to get on the test example. Looking at the upper bound doesn't really tell us how well this model is going to work well, right? We always want to be, when it comes to evaluation, pessimistic. Of course, when you're doing a reinforcement learning and then during training time there, you have to be optimistic, because otherwise you can't really explore the state space. But that's completely out of the context of this talk. So if you have any questions, just talk to me, but I'm not going to go into the detail there. So then how do we select the hyperparameters? In order to select hyperparameters, we need to have the hyperparameter the selection criterion. There are so many different ways, or there's so many different criteria we can use, and then we tested a lot of them. But most importantly, most representative, just two most representative ones include k-fold cross-validation. That is, we look at a very small number of the examples that were given to us, we partition them into the k-folds, and then for each fold, we use all the remaining partitions to train a model, and then see how well that Fuchsia learner work on this new, the original fold. And then we do that for every single fold, and then look at the average. The second one was minimum description length. This one is based on our work that was presented at ICMO earlier this year called Reason and Data Analysis. Here, instead of making k-fold and then trying to look at every single fold and then look at the average accuracy, instead, we look at the online coding accuracy, or how much we can compress the data using a particular hyperparameter. Unfortunately, I don't have time to go into the details of, in particular, the second one, but the important thing is that we really want it to be thorough and then try as many criteria as possible for hyperparameter selection. But whatever we do, I have to just say one thing before I continue and then present you with the experimental results. Prompt engineering is a very difficult problem a priori. Before looking at anything, we know that it is a very difficult problem. Why is that? Because the space of prompt is identical to the space of natural language. It's combinatorial. It's a gigantic space. The size of the space grows exponentially with respect to the length of the prompt that we're going to create. And then as we're going through this ongoing pandemic, we know how quickly the exponential function can grow. And then prompt length may change from one to another, which makes it even more complicated. And then furthermore, how to place the examples and in which order may impact the performance of the Fuchsia learning with GPT-3. And if you think about the ordering or the permutations of the training examples, however small of them there are factorial number of permutations. That's not that great. Right? So for our experiments, just like we don't even try to find a novel prompt from all possible prompts. Instead, because that's just impossible. Instead, we rely on a set of predefined prompts. Some of them were just carefully designed by people. Some of them were used by all their studies. What that means is that we are still going to be too optimistic. We're going to be optimistic when it comes to the accuracy that is being estimated. However, compared to looking at a very large number of labeled examples for the purpose of model selection, we are definitely measuring something much more realistic. It turned out that even with all this setup, it's not perfectly clear what should be done, or what are the things that we need to answer. So we tried to write down 3 major questions that we want to answer. The first question is whether we can identify the prompt that would have been used had we had access to a lot of labeled examples for prompt selection. That is, can we actually do as well as having a very large validation set while constraining ourselves to be much more realistic and having to have only a very small number of training examples? Second question is how likely we can do Fuchsia learning better with a prompt selected by or selected using only a small number of examples compared to a randomly chosen prompt. In other words, we know that selecting this prompt from this exponentially large space using only a few examples is very difficult because of the noise that arises from the fact that we are using only a small number of examples. But at least, can we do better than choosing a random prompt? It sounds pretty obvious that we should be able to do so, but at the same time, if you think about it a bit more carefully, is it really the case? Maybe, maybe not. The third question is trying to figure out the gap in the accuracy between the prompt that was selected using the validation set and prompt that is selected using only the few examples that we are allowed to use in true future learning. It's pretty clear that using the large development or the validation set is almost always going to be better, but perhaps the gap is not as large as we, or at least I was concerned about. So let's see, what kind of experimental setup we have. So we are going to largely rely on the first set of experiments, the data set called Llama, that was designed and released by Pretrained in 2019. It is a benchmark for retrieving facts from a language model. And then we use, a particular split named T-Rex. It has 41 relations with up to 1,000 examples each. And we use a subset called Llama unhelpful names that was a subset designated by the Poiner et al. 2020. And as a candidate prompts, we use manually curated prompts from the Llama paper as well as automatic paraphrases of these manually curated prompts from Alpaca, which was proposed by Jiang et al. In 2020. So it's pretty standard setup for checking the future learner or future learning from these language models. Now let's try to answer the first question. Can we identify or figure out the best prompt? Given only a few examples without any extra validation examples, it turned out that the answer is effectively no. Only with less than 30% of chance we are able to recover the best prompt that was selected using a very large extra validation set. And unfortunately, this was getting more and more difficult as the underlying language model got larger. What that means is that if the language model is large, there are many different ways in which we can prompt or instruct this language model, and then the chance of selecting the best one goes down. Furthermore, it turned out that at least up to 40, the number of training examples really didn't matter. Having 5 training examples was just as bad as having 40 training examples. What this means is that indeed, if we only have a few examples, we can't really do hyperparameter selection as well as having access to large validation example. Now, why does that matter? Because if we had a large validation example, what I would do is to simply use that large validation example set or a large subset of that as a training set, and then just fine-tune the entire thing. Why would I try to waste them for selecting just prompts, right? Now, let's look at the second question. Can we do better than a randomly chosen prompt? Again, given only a few examples without any extra validation examples. Now, it turned out, unfortunately, again, that we can do better, but only barely, and with a very, very high variance. So we observed less than 20% relative improvement. However, the variance was so high that in many cases, we saw that the carefully selected prompt may do worse than randomly selected prompt. And this is pretty much a bad kind of news, is that if we could just curate some of the prompts somehow, which we don't know how to do, but somebody told you, then the best we can do is to simply choose any one random one of them and then hope that that's going to work well. And it turned out it's not only specific to Llama. We saw the same trend in the case of the second question across multiple data sets. What that means is that we really need some extra information beyond these few examples in order to choose the prompt better. Now the third question, that was how much we lose with true future learning. Now, fortunately, the answer here is not as gloomy as the answers to the first two questions. There is definitely a gap between the prompt that the accuracy we get using the prompts that we choose using a very large validation set and the accuracy of the model that used the prompts that was selected using k-fold cross-validation or MDL. that is using only a small number of examples. There is a gap. However, overall, generalization performance increases as we have a larger model. So that's a pretty reasonable thing. That's a good thing for some data sets. However, still, we could do no better than simply choosing a random prompt from a very well-curated prompt set. And this curation was done using a very large validation set, don't forget. So in a sense, we are still overestimating the accuracy. And there, in this overestimation scenario, we couldn't do any better than just random selection of the prompt. In other words, if you're going to really use it for the real future learning in the deployment time, for your real purpose, very unlikely that you're going to be able to find the optimal prompt that's going to do really well for you. That's a bit of a sad reality. And obviously, one might think that maybe prompt engineering is not a good way to go. Just because the prompt space is so large, maybe that is the reason why it's not working well. So we try something else, that is trying to fine-tune the model or trying to fine-tune only a small part of the GPT-3 or the large-scale language model on a few examples. Now, unfortunately, even here, we're not free of the hyperparameters, but we need to tune the hyperparameters for these optimization algorithms that we use. And it turned out that, again, in the true fuchsia setting, we really cannot do as well as using a large validation set. And the interesting thing is that we realized that all the previous work, essentially, studies have reported the overly optimistic estimate of how well these models work or how well these algorithms work. If they stuck to the true fuchsia learning, they would have reported a much lower accuracies. So there are some somber realizations. Even with GPT-3 or these large-scale language models, fuchsia learning ends up being very, very challenging. And then if you think about it, it's not too surprising. It just cannot be easy. Fuchsia learning is not supposed to be easy because we only have a few examples. There aren't enough signal to train a new model. There aren't enough signal to find a good hyperparameter configuration. We need something extra to find a good hyperparameter configuration. And then that's what exactly the original definition of the fuchsia learning, as well as meta learning, transfer learning are. They all require having some kind of meta training and validation sets. Of course, there are different ways to approach this. One way to approach it is to view the prompt engineering as an inference on a unobserved variables. However, unobserved random variables, they're combinatorial. We don't know how to do inference correctly there either, so it's a very difficult problem. It continues to be a difficult problem. However, I want to at the end of my talk with a bit of a more joyous, let's say, observation is that it's still extremely exciting. When we think about neural network or the deep learning and then symbolic AI, often people's mind immediately goes to, okay, we need to somehow incorporate this symbolic logic or the symbolic AI into the neural network so that the neural net is able to perform these more traditional or conventional logical reasoning. However, what this GPT-3 or language model-based fuchsia learning or learning in general tells us is that we could have a fully deep learning-based execution engine that's going to be our language model, and then symbolic instruction can come in as an interface between us, the users, and these large-scale language models that are neural execution engine. By looking at fuchsia learning with language models as a symbolic instruction plus neural execution, we can now think about another way to approach this problem of fuchsia learning with language model. If we are provided with a few examples, that becomes essentially the program induction. If you're provided with description of the problem, then it becomes a program synthesis. What is the right way to write an instruction that's going to make GPT-3 perform what we want it to do? Perhaps this idea of fuchsia learning with language model will truly withstand the test of time, as was mentioned by the NeurIPS 2020 Best Paper Committee, is to be seen, but I do believe that it is very extreme. It is extremely exciting direction. However, we have to be very careful when we think about what we are reporting, what we are experimenting with, and what are the things that we say are possible. And then that actually concludes my talk, and thank you very much. So let's see.
Are there any problems? Yeah, so can you hear my voice, Kyung-hyun?
Yes, I can.
Yeah, good. So thank you, Kyung-hyun. So we now, thank you for the good presentation. And then now we'll go ahead and take some time for questions now. So just a reminder, please be sure to type your questions into chat window. So let's see the chat window for the question.
Or maybe my talk was too clear that there's no other questions to ask.
Well, yeah, I thought I have one question, but I'm just waiting for the questions from students.
I see. Okay. Sounds good. Yes.
But yeah, I mean, so because of the time limitations, so I actually gave one question to you with relate to the presentation. Okay. Well, I'm just curious about that. Where you know that you mentioned about the fusion learnings, GPT-X, where maybe the 4 or 5, I don't know exactly, but can we also observe the similar symptoms or the observations from other kinds of the artificial intelligence models, such as the computer visions or the multimodal learning part? So is it a similar, or I mean, are there any kind of difference in terms of the meta learning? I know
right.
That kind of area we have some kind of the meta learning and then the transfer learnings, and the hyperparameter computation is also one of the big challenges. So I'm just curious about what's your opinion about this question.
Right. So I mean, that's actually a really great point. So why are we actually talking about importance of this kind of, let's say, the formulation of meta learning or fusion learning in this context only? And that, wasn't there any issue in computer vision or audio processing or whatnot earlier? It turned out that that has not really been an issue there. And one of the reasons why it has not been an issue is that in those domains, it's very clear what is an input and then what is the description of the problem. And then they are extremely separated. You cannot really describe the problem of object detection using an image, right? The problem exists. So the problem description exists separately from all these problem instances that are images. Now, on the other hand, what is really fascinating about natural language is with language, we can express ideas. And what that means is that we can express the problem itself as well as example instances of that problem. The boundary between these two things is extremely fuzzy, and one might even say that boundary doesn't exist. And that is the reason why it becomes much more tricky to define this fusion or the meta learning in the context of fusion learning with language models, because we can't really tell the difference between them. And then that kind of, let's say, gives us as a humans, the natural language users, a bit of an illusion that we are doing fusion learning, although strictly saying people weren't doing the true fusion learning back then. And then what this work essentially says is that it's all fine as long as, but we have to be very careful in defining the problem itself, and then follow the well-defined notion of the problem in order to report correctly what is possible and what is not possible.
Yeah, that's right. So that's why I'm just curious about the multimodal part, the image and then the text together. Then maybe we can also find the similar observations. And then, yeah, thank you for your answers, and then thank you for your insights of the fusion learning in the natural language processing area. Yeah, so
okay.
So one of the questions, one of the questions.
Oh, yeah, I see the question there.
Windows, I'm just saying about it for the listeners in YouTube. So can we also design a general model for multi languages such as Korean, English, and other languages? What's your opinion about that?
Indeed, yes. So there are already those multilingual large-scale language models that were released from various companies, including Naver in Korea as well. In fact, I'm not sure if they released it, but yeah, they have built it themselves. And then the interesting thing about these neural language models or the large-scale language models is that the technology behind, so the algorithms that are being used to build these language models are language agnostic. They don't really care which language we are using. And in fact, it can very well be a corpus that consists of text written in multiple languages. That's all fine. Already in 2016, in some of the early papers on multilingual machine translation that I have authored together with my collaborators, we saw that we could train one machine translation system to translate from many languages to many languages. And once trained, these models were able to cope with the source text that is written in multiple languages simultaneously. So the code switching, so that happens in social media quite a bit. And then these models were able to seamlessly translate the source language as if it was written in one language into another language. So what that means is that these language models are built upon the foundations or the algorithms that are language agnostic, and that makes these approaches much more scalable across multiple languages in the world. So it's very exciting to see how well these models are going to work for these low resource languages by benefiting from the knowledge embedded in the high resource languages.
Yes, that's right. And then we take one question. Lastly, so then do you have any opinion on the best way to train a large model with few-shot learning when the training set is just too small to train on large parameters? So what do you think about?
Right. Yeah, that's a very, very good question. So that's what essentially, that's where we go back all the way to the original definition of few-shot learning, is that where do we get the learning signal? Where do we get the signals about the patterns that are embedded in all this data? Right? And then if we are truly given only a few examples, we can't really do much. The best we can do is to do the nearest neighbor classification. That's the best way we can do. However, then the idea is that we need to collect a lot of other data that are not directly for solving this particular problem, but they share some similar structures. Then we can now train a few-shot learner that learns to extract those patterns, and then when applied to this new set of few examples, it can extract the patterns from these few examples much more rapidly. So that's the idea of the few-shot learning as well as meta learning. So the answer is that we still need more data. If you only have a very few examples, you can't really get around with those few examples. You have to collect more data. But what is the better and more efficient and more effective way to collect data? That is the thing that then needs to be studied or investigated further.
Yeah, I see. And then so next, so we have a little more time to do the courses. So the next program will start 11:05. So and then there is one question from students, I guess. So the Professor Kyung-hyun Cho, so how could you get the ideas or the inspiration or insights for your research?
I see.
How about can you do the answer for the students?
Unfortunately, I don't have the answer because I'd love to know where I can get some ideas or the insights. And I don't think that I'm particularly good at coming up with the ideas or the insights. So I'm more of a let's be careful kind of researcher. So I read some papers and then I always ask a lot of questions myself as well as to the people who have read the paper together with me or even the authors on the points that are unclear. Because surprisingly, a lot of the terminologies that we use are not really well defined. But that's fine. We can talk about all this, let's say, big things like the AGI, like the few-shot learning, all these things. We can use those words, terminologies without, the clear definition in everyday conversation. I can talk about what AGI might look like together with you, like the Chin-young, without having to define what AGI is. However, when we do science, we have to be much more careful. And then, I try to be really careful. For instance, some of the students always just throw term the inductive bias to me. So whenever they have some, let's say, results that show that is positive, but that they couldn't explain, and I ask them how could we get this kind of results? They always resort to say that there is a better inductive bias in this approach, and then that's like one of the worst kind of possible answer to me at least. So I always probe them that, what do you mean by inductive bias? And in this particular case, what is that inductive bias that you have encoded? And then almost never the students have answers immediately, right? So it takes time. So what that means is that what I'm trying to say is that I don't really have any other things that or activities that I used in order to get the ideas or insight, but it's mostly reading others' work, others' papers, or my own papers, even earlier papers, and trying to see what were the things that were not well defined or not well formed. And then I try to define them better or form the question better, and then try to answer them. Or if the answer was incorrect after revising the question, then I try to come up with a better answer as well. So that's what I do.
Yeah. So thank you for the question. Thank you for the answers for the question. And then now it's time to wrap up. Sorry. And then thank you for the presentation and answering for the question one more time. So thanks again, Professor Kyung Cho. Sorry. And then thank you everyone. Yeah. And then we appreciate you being here. And thanks again joining us this program. And then we will have a break time 10 minutes. And after that, so the next program will start 11:10. So thanks again, and then see you. Bye-bye.
Bye-bye.